Unmute. Okay. Well, good afternoon, everyone. Thank you for taking the time to attend this seminar. Before we begin, I would like to begin by acknowledging the traditional custodians of the land on which we meet and pay my respect to their elders past, present, and emerging. My name is Mortaza, and I am the training coordinator for the Australian Space Data Analysis Facility. We have a very exciting presentation today. But before we begin, I do want to go through some housekeeping stuff. First, this event is recorded. We have a live, as in an in-person audience, as well as an online audience. And if you're joining us online and if you have any questions, please feel free to put it in the chat area, and then we'll go through the questions at the end. Our speaker today is Professor Gretchen Benedix. Gretchen is a cosmic mineralogist, astrogeologist using the chemistry, mineralogy, spectroscopy, and petrology of meteoroids to understand the formation and evolution of asteroids and other planets. She got her PhD at the University of Hawaii in 1997. Her thesis unraveled the geologic history of a rare group of meteoroids that offer a snapshot into planetary differentiation processes. After this, she held a number of postdoctoral positions that broadened her knowledge base from determining the surface composition of Saturn's moons to looking at how water, ice interact with silicates on small bodies. She has worked at both the Smithsonian's Museum of Natural History and the Natural History Museum in London as a researcher. She joined Curtin in 2012 as a senior lecturer. She was awarded a senior Curtin Research Fellowship in 2014. She currently holds an Australian Research Council Future Fellowship and is a member of the Space Science and Technology Centre in the School of Earth and Planetary Sciences. Professor, over to you.
The whole thing. Thanks very much for having me today. I appreciate it. Thanks for coming out. Since we're a bit cozy here, please feel free to just shout questions. This is going to be more like a conversation. I'm gonna just offer that as an option. I've given this talk several times, so different audiences get slightly different versions. This particular talk. Do we want the microphone muted still?
So we're just using the microphone and the laptop. So.
Okay, cool. All right. Sorry. It was, yeah. So my work, so we were talking about the thing that Mortaza just read off is the work that I used to do a lot more of. Since becoming an ARC Future Fellow, I've focused a lot more on looking at the surface of planets rather than focusing on the rocks. I have a student who's looking at the rocks still and dealing with the spectroscopy, but my whole background is pretty much about wanting to understand the evolution of the solar system as a whole. So I have a very much sciencey, curious, want to answer questions about where we came from kind of background. So where this comes from is that we want to try and understand what other planets tell us so that we can understand what's going on with Earth, because Earth is a very volatile, very active planet geologically. So the surface is constantly changing and getting eroded away, and mass is being added. So what is happening now on Earth is not what happened 4 billion years ago. And if we can understand what happened 4 billion years ago, we might have a better understanding of what's going on here and now. So basically what I'm trying to do is understand what is going on another planet by not actually being a geologist and going there. Because as a geologist, you want to go to your field area because it's really important to be able to go and pinpoint the thing that you are looking for. But because space is hard, because getting people into space is hard, we have come up with a lot of really innovative ways to look at other planets and try to unravel their histories and try to unravel what we can learn about them. So we have 60,000 rocks on Earth that we know come from other places. Most of them come from asteroids, but about 150 of them come from Mars. Mars is a really interesting planet to have a look at because it's our nearest neighbor that's close to a habitable zone, which means that there's a possibility that you could get liquid water there, especially in the past. But we need to understand more about that past. And so what we're actually trying to do is understand the history. We need to get at that. To do that, we need to know what the ages are. Ages are a massively important part of geology because you put things into a certain order, the way things work. If we want to go out looking for resources, particularly petroleum, we are going to be going to look at very specific age ranges of geologic features. So if we can unravel that, we can actually get a much better idea of the history. So on the map here is just showing what Australia looks like in terms of its geology, but a lot of this geology is not just rock type, it's age as well. And so that gives us a different kind of idea of what Australia is like. So that's why I've included that. But what I'm coming at here, what I'm describing here is a way to determine ages. So that's what we call in rock science geochronology. So geochronology is about determining the age of a rock. We can do that chemically. We can use radioactive isotopes of elements to determine that. And different pairs of radioactive isotopes will give you different ages. So they date different things. So if you can get a whole bunch of these ages on a rock, you can kind of unravel a whole really interesting history. So this particular example here is from a rock, which is one of the older rocks from Mars. But by analyzing all these different chemical pairs, we've been able to determine when it was formed and crystallized. We've been able to determine when it got buried. We've been able to determine when it started to feel another layer of heat, so it got some metamorphism. We've been able to determine when was it excavated and brecciated, like crushed all together, and we know exactly when it was launched off the surface, all by looking at these different geochemical things. And there are error bars on this, but the error bars, it's like astronomical terms. They seem like big numbers, but relative to the other big numbers that we have, those are really tiny. So we're looking at billions of years here. So things go back to 4.5 billion years, but we think that we're fairly confident that it was ejected about 3 million years ago. So there's some really interesting thing we can do this with this data, but we have no idea where these rocks come from on the surface of Mars. So like when I'm talking about being a geologist, you want to go out there, figure out where you are, pick up your rock, take it back to your lab, do all the things, and then you can go back and put that rock in place and say, all right, here's my volcano. I know this part of it is this age. That means this happened here and this happened here. And that means when I'm going to look for a thing, I want to focus over there. We have no context like that for meteorites. So we have to do geochronology in space. So we use a technique called crater counting, which gives you relative ages. So with radiometric dating, we can get an absolute age with a certain error. But this gives us the idea of what came first and what came second. But if we want to be able to match that, so instead of being able to say that area is older than that area, which we can do very straightforwardly, we want to be able to say that area is 4.5 billion years old. That area is 3.25 billion years old, not just older or younger. But we need, in order to do that, you need a rock from that space. So one of the things we can do, this is just to show you, this is a picture of Mars flattened out, the whole globe, showing you elevation. So this is just illustrating the various elevations on the surface of Mars. It goes from, I don't know if, can you see that? You can see that. So this spot here, that's Olympus Mons. That's the biggest volcano in the solar system. It goes up to about 29 kilometers above the surface. And this hole over here, this crater over here, that's called Hellas Basin. And it goes down to about 8 kilometers. So there's this massive difference in height. But interestingly, if you look at the northern hemisphere is a lot lower than the southern hemisphere. And what you can see on the southern hemisphere is a lot of craters. You see a lot of really rough terrain. So this is just illustrating why crater counting works. We know that the northern hemisphere doesn't have nearly the same number of craters as the southern hemisphere. We know just by looking at this that something happened on the northern hemisphere. It's a younger surface overall. Not just is it lower, it's actually younger. We don't see the number of craters. So that's already giving us a hint that something really interesting happened after the planet was formed and had experienced a lot of stuff. So if you are using crater counting, the whole idea behind the theory is that if you have a surface and you have a known impact rate, over time, that surface will continue to accumulate craters. And if you can do that absolute calibration, which we did for the moon, so astronauts went to the moon, they picked up rocks from very specific areas, brought them back, we could then match all that crater stuff to the ages. So then we can do some really nice little hand wavy things and say, okay, well, we know that age works for the moon. Now we can do some really nice maths that has to do with physics and basically how do rocks move. And so if you get closer to the asteroid belt, which is where your stuff is, what's the energy going to be like? What's the gravity of Mars going to do to the escape velocity? How is that going to affect all your impacts? You can do all that, and then you can kind of shift all these ages so that when you do a crater count on Mars, you can actually kind of get back to an estimated absolute age. Okay, now that's really cool. But okay, so this is basically an example of what I've just explained, which I think you guys can understand. We've got time one, we have a few craters. The other thing that this illustrates is that the other really interesting part is that the sizes of the impactors are not all equal. So you have a range of sizes, and those sizes follow a power law. So you have a few really big ones and a whole lot of really tiny ones. So here's time one, you have one really big crater, a couple of medium sized, and a whole bunch of little ones. Time two, you have a few more of those things on. Let's say at time three, a volcano erupts and you get a lava flow that covers up all those older previous craters. And then at time four, you've got the impact rate happening again. So this is what we are able to do. So at time one, you could plot all this information up. You could look at the number of craters versus its diameter, and you have a line. Time two gives you a different line. So it just has more craters on it. Time three is, again, another one. But in this case, if we were to want to actually try and figure out what is happening in terms of when did that lava flow occur, if you then, instead of just looking at the entire area and counting everything, if you then decide, I'm going to block off certain areas and just count the craters across a specific area, then that area will give you the time of that particular event. So you have to be really careful about doing that. But when you do that, instead of getting three equidistant lines, you're going to get two lines that are closer together and one that's farther apart because you're looking at a resetting event. So these are not real isochrons. These are just examples to show how this process works. So this is just the theory behind the process. And this is just another way to look at it. If you look at for all craters that are about 1 kilometer across, this is how many you would expect at different ages. So at 4.5 billion years, you would expect to have a much higher number per area of these of these 1 kilometer craters than you do now. And that's because over time, all those little asteroidy bits start breaking apart and get smaller and smaller, and then you just don't have as many of them. And then this is the other way to look at it. If you look at, instead of looking at a single diameter, if you want to look at all the diameters, you get these various ages. So you can start to see how, if you can count things, so if you can get the total number of these craters and you know what their diameters are, you can start to get at different ages. So this line here is 4 billion, and then it goes down to 1 million. Now, this has all been painstakingly worked out using craters and they were all counted by hand. So since the 60s and since we went back to the moon, or went to the moon, the people who've been putting all this theory together and trying to figure out these power laws and everything have been focused on doing this all by hand. So they get these big maps out and they do things by hand. So we have to kind of talk about the difference between these things because, all right, some of this has been done by hand already. So what's the point of doing this more? We already have complete databases, hand counted, manually determined for every crater greater than 1 kilometer in size. Guy did it by hand, circled, measured, put it into a database. Took 6 or 7 or 12 years of his life to do it. His PhD was the Martian one, so that was 385,000 craters he counted by hand. That's all from 1 kilometer. Now, if we could automate this, we could get to much smaller sizes. And the smaller sizes you get to, the more accurate your dating can be and the more recent times you can get at, because the isochrons change with time. So we can really date well things that happened 4.5, 3 billion years ago. But once we start getting younger and younger to times where we might want to be able to see, say, we know that a meteorite has been in space for 3 million years. Where's an object on the surface of Mars that's 3 million years old? So getting to that smaller size is the important bit. But it's really actually quite hard to do this. So we wanted to give this a go with the crater counting. So this is a map of all the craters on Mars bigger than 1 kilometer. And the dots go relative to size. So the bigger dots are bigger craters. You can see, just looking at this map, you can see the difference between the southern hemisphere and the northern hemisphere in terms of total numbers. You can see this area here, which is really quite blank. That area is the youngest area of the surface of Mars. That's the Tharsis Plateau, so that's where the big Olympus Mons volcano is. This is Valles Marineris, the big canyon that goes off of that as well. Over here, this is sort of the Elysium area. It's also volcanic in nature. So that means that these are the areas that are constantly getting resurfaced. So they're much, much younger. There's also, we've got a whole bunch of rovers across here so we can see in detail some of these things. It's really hard to count craters, even so if you're doing it by hand. There's humans lose focus after about 30 minutes. So this guy did it for 6 years. He's literally circled craters on maps for 6 years. So there's a good chance that he missed some. There's a good chance that he misidentified some. But there's also an idea that if you take the same map and give it to 2 different people or 7 different people who are all experts in crater counting, they'll all come up with different numbers. So what we wanted to try and do was we want to get to small numbers. Small numbers means we're going to be in the tens of millions of things. And we wanted to make it as accurate and repeatable as possible. So this is where this crater detection algorithm comes from. So we were basically using a convolutional neural network. I think, Vlad, you've seen a lot of this already. This is the best way to apply this work to images. So we were basically trying to do object detection. So I guess it's very similar to some of the galaxy machine learning, trying to figure that stuff out. We used something called You Only Look Once, YOLO, which was devised a few years ago. And it's a really great methodology for supervised machine learning where you can train it to identify different things and then run a picture through it, or use it on an image, and the image will detect different things in it. So we did this on a relatively low resolution version of the Mars global map, which is called THEMIS, which is basically is a thermal emission map that allows you to see different craters because of the way the rock type radiates heat away. So we can use that, but that has a resolution of 100 meters per pixel. And so that's the map that the guy who did the manual counting used. And so most of his stuff, so we could use that as our testing ground. So then we could take that, see if we could repeat and get what he got. But then we wanted to apply it to a much higher resolution data set. So there's a roughly, it's 5 to 6 meter per pixel global data set, which is much higher resolution, means that you can analyze things that are maybe 50 meters across really, really well. There's another data set called high rise, which is 30 centimeters to a meter per pixel, which is really, really high resolution, not global in any way. The data rate from Mars to Earth is way too slow, and those images are massive. So those are very much point and shoot kind of places. So you pick a place you want some really high resolution imagery of, and it's usually the best landing site options for the next mission. And then you can get the high rise data. So we've used a combo of that. We basically trained it using images, and this is like the basics of the modeling. So you take an image, you cut it into a bunch of tiles, you analyze on those tiles manually. You still have to give it a manual data set. So we manually counted a bunch of stuff. Then you can do augmentation where you flip everything around. And so we had a training data set and a validation data set after that. So you start with training, you get a bunch of squares around circles, and it's really surprising how hard it is to teach a computer to find a circle, you know, because humans are trained to look for circles and computers are like, well, where are the lines? And so this works really well. It gets trained really well. We had a validation data set, and so we ended up with a pretty decent precision and recall. And so basically we knew that if we put this in, if we put an image in, we should be getting something pretty close to what multiple humans would produce. And the beauty of it is that in our initial run, it took us about 15 minutes. We figured out that if you use a JPEG instead of a PNG image, you can drop that down to about 1.5 minutes per little image. So your count time goes from, and this was for images that were, here it says 26,000 by 17,000 pixels. It would take 15 minutes. We got it down to 1.5 minutes for those. So this is what's awesome when you can run things with in parallel with a GPU, have access to the POSI supercomputing center, all really awesome stuff. So then you have to have a look and see how it works. How did it do? So in this, this is a comparison of the manual to the automatic. Ours automatic is red, manual is blue. And so you can see that there are lots of places where they overlap, and they overlap pretty well. There's some places where something, you know, the manual picked something and the automatic did not. And that's most likely related to the fact that these are probably hidden or degraded. And so the expert can maybe find something that we haven't trained the machine to do, or the expert just got it wrong. And those are not craters at all. So the other thing is that these are craters inside of another crater. So that's another interesting thing. So we trained it specifically to look for craters less than 1 kilometer, because we know all the kilometer and bigger ones are out there. But on our test set, we had that to make sure we would overlap with the manual. So our differences here, we wanted to show that when you lose resolution, the smaller your crater gets at this 100 meters per pixel resolution, you're still getting a roughly close in terms of center point, but your diameters can change, or you kind of offset the actual center point. But overall, that doesn't happen until you get down to about 1 kilometer in terms of the crater size. This was how we tested it. We looked at the entire surface at this 100 meter per pixel data set. This is the original manually counted data set A. Ours is the CDA down here. And if you look at those two maps, you can see that they're pretty similar. And then what we did was we did a difference. So you could see where things were overestimated, like diameters or latitude, longitude center points, or where they were underestimated. So where the CDA didn't count enough or found stuff that wasn't there. But what you can see is that roughly through the center latitudes between plus and minus 45 degrees, we're within 20%, which is well within what different humans would produce. And this is just another way to look at it. If you look at it in terms of the sizes, you can see that overall in the region we were interested in, we were pretty much hitting the mark. So we said, this is great. So then you have to test it on unknowns. So you have to run it, and then you have to look at what's been previously published to see if you're matching it. So this image back here is called it's a quadrangle called Syrtis Major, and it's just a big area of Mars. It's pretty heavily cratered. And so what we did is we counted everything on that automatically, and we compared it to what the manual database had. And so we've got the green and the red lines are those two differences. And basically they're overlapping, and they're showing that the age of this surface is going from roughly 4 billion to about 3.75. And that's completely consistent with what we can see there. We're seeing a lot of heavily cratered areas. That makes a lot of sense. So that was good. These are a couple of areas that are much closer in. These are in the Gusev Crater. So this is where Mars Curiosity is roving around. So there were a bunch of different areas we looked at, and we wanted to look not just at the higher resolution, 5 meters per pixel. We wanted to look at how did it compare, how did it test with the really high 30 centimeters per pixel. And in some areas we got some good agreement, and then in other areas we got, and it's all related to the resolution, so we could see how we were actually getting differences. And you can see these nice kinks in here which cross isochrons, which means we're looking at a surface that's going from like 30 million 100 million years old up to 4 billion across this one little region. So that's really, really interesting to look at. One more test to show you. This is just showing in certain areas of that Gusev Crater area, we're getting the same ages. So this is the age we calculated using our craters. This is the age that it's published. So we're well within error on all of these areas. And they were very different types of areas because we wanted to make sure that the algorithm is actually doing similar things to what we can see. This is where the Perseverance crater, or Perseverance latest rover landed, driving around. The main target area here is this thing, which looks very much like a delta. And so when space science people are going into find places to go look, we really want to find where the water is or was, because water is extraordinarily important. It's the main catalyst for forming life and getting cells to work. And so if we can find evidence for liquid water, there's a possibility that the chemistry would be there that could potentially have organisms. There won't be organisms on the surface of Mars ever, but they are going to keep looking. But the fact that we have all kinds of water features means that we need to, these are the places we want to go investigate. So this thing looks like a delta or some kind of river outwash. So this looks like some kind of river that basically just came and dumped a load of stuff. But there's also a whole bunch of craters in here. So these are where we can use our crater counting to actually find different ages across the surface. This was just to show the main reason you want to do this, because if you can go to different higher and higher resolutions, the number of craters you're going to count is just going to increase. So this is for the entire area across this region. If you just look at the 100 meters per pixel resolution data set, you get 8,000 craters. You have 112 that are bigger than 1 kilometer. So if you were plotting all these up across this area, you'd get an isochron that went a certain way. But if you were on this specific area, your 1 kilometer crater, there's 112 of them. If you can drop into this area with a much higher resolution, you're going to start to build up your total numbers. So in this case, we had over 3,000, almost 4,000 that were bigger than 100 meters. So there are only 112 that are a kilometer across, but having 3,800 at 100 meters to 1,000 kilometers really opens up that whole timing feature. And then if you zoom in at the highest resolution, you can go from 29 that are greater than 100 kilometers to 1,000 that are greater than 3 meters. So you're just really opening up that whole area. And then that allows you to get at different, allows you to get at a rough age of the base of that crater, which is around 2 billion years. So if this water is coming in, that surface was there about 2 billion years ago. So this water is happening after that. So we got that. So let's go back to the manual counting just to show you. So we published all that. Algorithm works. Yay, awesomeness. Fantastic. Remember that my goal as the astrogeologist is to figure out where, potentially figure out where do the meteorites we have on Earth come from on Mars, so that I can take the ages and everything I know about the meteorite and stick it in a place on Mars. So we have to do this. So here's our original manual counting image. We analyzed using the CDA and retraining it only a little bit using higher resolution imagery. And we ran it on the entire CTX, so 5 meters per pixel global, which is about 13 terabytes worth of imagery. We ran it, and this is the map that comes out of that. So this is, these are craters. This is not, every dot on here is a crater. These are craters between 50 meters and I think 300 meters. So these are all the smallest craters on the surface of Mars. This is 90 million craters counted on PASI in 24 hours. So the CDA works. It's kind of cool. So when I looked at this map initially, I thought, wow, there is a lot of stuff here that I've never seen before. Because we normally look at these either optical images, or we look at these emission images, or we looked at that original crater counting map where, you know, there's nothing happening over there, right? Nothing happening in this Tharsis area, which I can't make my mouse go there. And now there is just a lot of structure there that we hadn't ever seen. And people have seen some of it before, but the manual counters, they're sitting there and they're gathering all these images and going point by point. This gives you like massive, you've got the image right there. And the thing that's awesome to note about this is that there's this, I'm just going to walk over here. Okay? This guy here is really interesting. And this one here, you can see these rays coming off of it, or here, the rays coming there. That indicates a young crater, because all those rays are formed when the crater forms, material splashes out, and all the material that splashed out that doesn't reach escape velocity falls back down, and it leaves more craters that we were able to count. And the distance of those rays is really interesting, but the fact of the rays means those are the youngest craters. We can go in now and we can target those specific areas to figure out how old those craters specifically are. We know that they are the most recent craters formed on Mars, which means they are likely the most, they're the most plausible launch crater. So they're the most plausible point where the source meteorites would be coming from. So that's what we did. We focused in on that one over by Olympus Mons. It's a crater called Tooting Crater. It's been talked about for a really long time. The original data, so the crater is there. The original discussion of it, scientific study of it, mapping of it, had the rays going to about here. So we can see that the rays are going 1.5 times farther, which tells us something about the energy of the impact, which is interesting, which means there's enough energy here to launch stuff into space. But we also have this really cool feature here. That tells us there's an area there where there's no crater, there's no ray. So that tells us that this was an oblique angle. So this hit at an oblique angle and tossed a lot of material out there. So we started looking at this. No, go ahead.
If you had the resolution that that ray would go halfway around the planet or something?
That's a really good question. It goes about 1,500 kilometers away, and the radius or the circumference radius of Mars is 3,000-ish. So the circumference, so yeah, so it doesn't go all the way around, but it goes a lot farther than initially thought, which means you've got an interesting kind of range there. The size of the crater itself is about 30 kilometers across. And so we started digging into this because this was really showing us that there's something interesting happening here. My postdoc, who's Legane, he's the author of the paper, but together we've been looking at it, trying to figure out how do we get at the ages? Because we need to get at different types of ages. So we know this is a young crater, but we need to know how young is the crater. But not only that, in order to match it to any meteorites that we have, we need to know how old is the surface that was impacted nearby. The other thing about this that's really, really cool is you can see just from the crater, you can see that's Olympus Mons, another one of the volcanoes, Tharsis volcanoes. See all of that feature just from the crater imagery, the crater density. You can even see the caldera of Olympus Mons just by mapping craters, which is kind of amazing. So this is the sort of close-up of the crater. It's, like I said, it's 30 kilometers across. It's a complex crater. It's got a central peak. That means that it was big enough that mantle materials were rebounded up after the initial shock wave. There is, oh man, sorry, that little picture should go somewhere else. This is the original mapping done. So this is not a map of rock type. This is just a map of where people saw lava flows end here, lava flows or ejecta blanket ends here. So this really is just a feature map, which is really helpful. But we were able to take this so that we can identify the areas that are the same that we can use to date. So we can say this area is all one. We know the age that we count off of this is 1H. This image that you can't see very well is how we were looking at comparing the meteorite ages to the crater ages. So these are all different craters, all these youngish craters. They have the rays on Mars. So we dated them, and they all have these. This says impact crater model age. So that's the age we think the crater was made. Then we also have something called surrounding ground. So that's the age of the target rock. And so if we plot those things up, we should be able to find a sweet spot where the meteorites' ages match. So when we did that, we got this line of craters up here. So there's something going on. We got really old surfaces, old surface ages, and a whole range of launch ages, all relatively young, all in the last 10 million years. But that doesn't fit with our youngish meteorite ages. And so we found this guy down here. And so this kind of hit our sweet spot of an area where we should see something, and that's Tooting Crater. So we dug into that a bit more to try and get at the understanding. And we're relatively sure, well, we're like 95% confident that that is the source crater that launched a subset of Martian meteorites. We can now say that by putting the meteorites in that crater, we now know more about the Tharsis magma system volcanically. So what we've done is we've been able to take something that would have been impossible, applied a detection algorithm, a mathematical algorithm to imagery, and extract an amount of information that has just changed how we can look at the surface of Mars. So from the perspective of a scientist, I'm like, woohoo! But this stuff is completely applicable to anything that's image-based. And so we've been working with a couple of industries trying to get some where the imagery is similar and seeing if we can do some crossover on all this automatic, using this kind of automatic algorithm, counting algorithm. We're also in the process of applying it to the moon and to Mercury, because one of the biggest questions that we have in space science and planetary science is, how has the rate of impact changed over the lifetime of the solar system? Jupiter did this really big swing. We probably wouldn't have life on Earth without having a massive impacting bodies coming in, but we don't know how it changes over time exactly. So this data set is going to help us dig into that, and doing it at Mars, at the moon, and at Mercury gives you not just that spatial, you'll get the spatial resolution as well. Anyway, there we go. That's all. You're welcome.
Not sure if this is a question that makes sense, but I guess that there were 140 that have been recovered, and I guess some portion of them, how how old they are, and roughly where on Mars they might have come from. To what extent does this new crater map allow you, out of that 140, like,
How many?
what more is a significantly improved idea of where they...
Well, it does a couple of things. One is, it's because it's a subset, so it's a small number of them, but it tells us about the temperature of the interior. It tells us about the depth of the interior, so we know when we study the surfaces of planets, we don't know anything about the interior. When we study Earth, we have earthquakes here, we have seismometers everywhere. We can get an idea of what the interior of the Earth looks like. We know how much heat is coming out. All of that feeds into our climactic cycles. It feeds into how we go looking for things. It feeds into the general chemistry over the billions of years that has actually, put resources into very specific places. Because if you look at the most primitive rock in the solar system, which is a chondritic rock, elements are just distributed randomly throughout. They are not in specific areas. You need heat, you need water, you need impact, you need something to move things around. So to get resources to be concentrated in very specific areas, you need that kind of motion. So if we can try to figure that out for other planets, that's a really interesting thing overall, not just from a resource perspective, but from a planetary evolution perspective. So those meteorites let us see into the interior. Right now on Mars, there's one seismometer, and there might be a second one that Perseverance is going to deploy. I think they have a mole as well, or a GPR or something. So that is one of the major areas where information is lacking about planets in general. We make a lot of inferences about planetary interiors using how they orbit other bodies. So if a spacecraft goes by a body, how it wobbles is directly related to how the mass is distributed in this big body.
Yes. Thank you for such a fascinating presentation. Can I just ask, with your detailed knowledge of the surface of Mars, do you ever have the opportunity to engage with organizations that will influence where future exploration rovers will be deployed?
I do have contacts with NASA. So this is the kind of thing where if we can say this is where these meteorites come from and it's a safe enough landing spot, there's a good chance we could influence that as a particular landing area in the future. But we're also able to say, okay, well, we know that your current rover is over here. We might be able to supply some new information about where you should go looking since you're there. Because that's one of the things, they haven't picked where they're going to pick samples yet for the Perseverance rover. So they're in the process and they want to pick areas. So they're kind of sitting there and there's a lot of mapping happening and they're looking at things. And they got their little helicopter kind of not really doing much, being a technical demonstration, which is awesome. They want to actually go up that river gully and go out of the crater. but they need to collect samples along the way. So our data might, if we're in the process of switching over to that and having a look there. But for now, this was the thing I told ARC we could do. And so we've done it. So I'm like, yay, I earned my money. Sweet. And thank you, taxpayer. So it helps us understand just more. It feels like we should know a lot about these other places. And we do, but we don't. There's just so much we have to infer. So getting actual like concrete data is really useful.
Any water bodies exist on the Mars?
Sorry,
Water bodies?
what is
Water bodies.
water?
Water bodies on Mars. So
Well, no.
because of some craters there.
Well, okay, so there's an idea. I go back to, sorry, it'll catch up. I go back to, it's there. It's almost there. Come on. That one. Okay, so if you look on here, there has been an idea. You can see that you're going from a very high area to a low area. So there's been a lot of discussion about how this could possibly be a big kind of outflow. And if you start looking at features up in here, up through here, looking at all these features around here, it's been floated that that was an ocean. There are a whole bunch of features that are very consistent with big bodies of water on the surface of Mars. The problem comes when you try to model how that could happen. The atmosphere is about 1/100th of the Earth's atmosphere and is 90% CO2. So there is water on Mars. It's locked in the poles. It's water ice. It sublimates and then it reaccretes to the poles, but it doesn't really spread around that much. There is a anecdote that says that on Tharsis you get frost, but it's gone by the time the satellites can take a good image. So it's like they think there was frost there. So there's a whole bunch of different things. The problem with the atmospheric modeling is that we don't know where the atmosphere went. There's an idea that there was a much thicker atmosphere in the past, which would give you the pressure you need to hang on to water, but that's gone away. So if you've lost that, then once your water evaporates, it just goes into the space. So it just goes away. So this is a massive question. This is why we keep looking for water. There's all this evidence that water was there, but we keep coming up dry, basically. It does exist, but it's just not in liquid form. And to get it in liquid form on the surface, because of the surface pressure, there's this really, really, really tiny temperature range that you have to achieve, which is right around 25 degrees. And it's just, 25 is like a massively hot day on Mars. It's mostly in the ice or gas phases.
Thank you so much.
You're very welcome.
Quickly check the
Oh,
chat
yeah.
area to see if anyone online has asked any questions.
You mentioned the moon, Mercury, and Mars. So data from Ceres good enough for the?
Yeah, we actually ran it on Ceres, which is really interesting. Ceres it's a small body, and we got an answer, but it was really hard to figure out. So we need to actually retrain using Ceres data. So we used the Mars trained algorithm on Ceres. So we can do it for Ceres, we can do it for Vesta. Those are both really good ones to do that we have high-res imagery for. There's not really any point in doing it on Bennu or Hayabusa. They're just too small and they're just covered in boulders. So we'd have to retrain to look for like boulder distribution or something.
We've got a question from Professor Lean Beasley. So loved every word and image. Thank you and congratulations. The question is, did Mars ever have tectonic activity? If not, why not? If yes, did this influence your findings?
Excellent question. Thank you, Lynn. The Mars is funny. It does have tectonic activity, but it doesn't have plates. So on Earth, we have a whole bunch of tectonic plates and they move around. And so there are fault lines, there's subduction zones, there's convergence and divergence. You've got all kinds of movement. On Mars, it's a single plate. So one of the things about it is that this crack here, so this canyon, Valles Marineris, that distance is across Australia. That's 4,000 kilometers long, right? This Tharsis area is almost like a Hawaiian hotspot. So if the Hawaiian Islands, if the Pacific plate never moved and you just had one gigantic Hawaiian island, it would just build and build and build and build. There's no water to speak of really on Mars. So the only way to compensate for this growth is to get this big crack. But that's the extent of tectonics. Tectonics on Mars is around impacts hitting it. But the rover, the InSight lander, which has the one seismometer, has now found that there is evidence of internal tectonics. But because there's no plates, there's no plate boundaries, you have no place for any of that. It just grows and cracks. It doesn't have you don't shift anything or move anything around. So so the thing that our work does help with is to understand that depth of that magma chamber. So because the crater is off the edge of that big Tharsis plateau, that big volcanic region, we know that, and because of the geology of the meteorites, the mineralogy and the chemistry that we can see in them, we know they come from deep. We can get an estimate on what pressure it is. We know from what Mars's depth radius is, we can kind of guess what pressure is where, and things are changing in terms of where we think that magma chamber sits. So it does add to our understanding of that interior, which is partly what we don't know a lot about. A really great mission to Mars would be to send a whole bunch of seismometers, but high resolution seismometers are really heavy, and until we're launching from the moon, I don't think that's going to happen.
Professor Lean Beasley just thanks you. So wow, and thank you.
Words.
I don't have any other questions online, and I think this is the end of the session. Thank you everyone online for joining us today. And thank you so much, Gretchen, for this talk. Yeah, so have a good evening, everyone. Thank you.